Hello, this is Mr. Craig, and this is part 2 of the same lecture, actually lecture number 1, day 134, examples part 1. And I just finished the calculations, and if you didn't hear me discuss this, I highly recommend you watch part 1 of the video. I do want to talk about or discuss the common ion effect. Now, we talked about this back when we were doing buffers, which was a while ago, and if you need to review that, I highly recommend it. But when we talk about the common ion effect, and I'll let you read over that, but I'll briefly discuss the common ion effect here, and I'll give you a couple scenarios. In the last problem that we just worked out, we calculated that we could dissociate almost about 0.45 grams of silver sulfate in 100 milliliters of water. Here's my scenario types. Okay, let's say we take our beaker of water here, and we're going to place the silver sulfate in there, and we're actually placing in 0.449 grams of silver sulfate in the water that has nothing in it. In other words, we have pure water. Here's some things that we should recognize or be able to observe, or at least be able to predict as we do these sort of things. If I place 0.449 grams of silver sulfate in pure water, what should I see in the beaker? In other words, once that goes into the beaker, what should I be witnessing? Or what should I observe from this? Well, once I place this into the solution, I should see all the crystals. As long as I weigh it out correctly and I have 100 mils of water and it's at 25 degrees, all those conditions are met, I should see this crystal totally dissociate 100%. And upon that, we have just made our solution saturated. So what that means is we have some silver ions and some sulfate ions floating around in the solution. And also that the solution is now saturated. And that's a huge term that we need to know, or that's a really important term that we need to know. Saturated means that we cannot dissociate any more of silver sulfate in that solution. So if I add, say, instead of the 0.449, I actually added a half a gram of silver sulfate in here. 0.449 grams of that would dissociate, and then I'd have about 0.05 grams of silver sulfate crystals sitting on the bottom of the beaker, or at least moving around on the bottom of the beaker after I've stirred it all up. So you'll have some excess. In other words, what that means is there's no way that this solution, upon becoming saturated, will be able to dissociate any more of those silver sulfate ions. Again, it's a very weak salt, and once the solution's saturated, that solution will no longer allow any more of that to take place. Okay. Now, let me give you another scenario. Let's say, let me erase this. Let's say that we have our saturated solution. Okay. Let me erase. Okay. Let me erase. And let's say that we're now going to place in here some sodium sulfate. Okay. In other words, I have my saturated solution of silver sulfate in my beaker here. Okay. And now I'm going to add some sodium sulfate in here. Now, here's something that's really, really important. Now, let's say it's just saturated. It doesn't have any excess in there. Once I place that sodium sulfate into the water, in other words, we drop it into the water, what will the sodium sulfate do, or the crystal itself? Make sure you know your solubility rules. This crystal will dissociate 100% upon hitting the water here. All that sodium sulfate is going to break apart. But what I want us to be able to recognize is if we do this, what will we observe after it has dissociated? Well, hopefully you're going to start to see some crystals forming on the bottom. And these crystals will not be sodium sulfate. Here's my question. What will those crystals be made up of? And think about Le Chatelier. Okay? So again, here's our balanced equation. This pen will write. So I have my silver sulfate. Okay. I have my silver sulfate. And it broke down into silver and sulfate ions. Now, common ion effect. What ions are now in this solution? Okay, what ions, I'm going to ask you, are in this solution now? Well, we do have silver, we do have sulfate, and we also have some sodium ions in here now. But recall, before we placed any of this silver sulfate in the solution, this solution was saturated with silver sulfate. So the crystals that are forming down here, I am adding a common ion. I'm actually adding more sulfate ions. So if I'm adding more of a common ion to a solution that is 1, at equilibrium, and 2, saturated, these crystals here are actually shifting. In other words, they're the formation of an addition of a common ion, which means that the silver sulfate, since I'm adding sulfate ions, they are going to shift away from the addition. That's Le Chatelier. So what happens is, as I add more sulfate ions, because again, recall, our expression that we wrote earlier on here can only hold a certain amount of silver and a certain amount of sulfate to have this value here. If I have this at equilibrium and then I boost the amount or the concentration of the sulfate, we have exceeded this value here, and it's going to cause the formation of a precipitate. Or it will shift toward the direction that will form solid particles to eliminate some of these ions in solution. So what's going to happen is the concentration of the silver ions will decrease. We'll lose some of these silver ions because of the increased amount of the sulfate. So as the sulfate ions are being introduced again into this solution, we're actually going to form some more silver sulfate. And then I have to ask you, well, what's the sodium doing in there? It is simply a spectator. It's doing nothing. So it, as spectator ions, spectators don't do anything. And besides, make sure you know your solubility rules, which state that sodium will not react with anybody. Okay. There's another scenario. So let's get rid of that. Oops, I erased. Let's see, what's another scenario I can give you here? Alright, one more. Let's say we've got our saturated solution. Okay, I'm going to draw this whole thing again. I've got 2.5 minutes so I can talk about it. Alright, here's one more scenario. Oops. Come on, write. Please write. Okay. Alright, we have our beaker. Okay. And we are saturated. And let's say that this volume right here is 100 milliliters. Okay. Oh, come back. So we have 100 milliliters. And again, it's still saturated. What will happen to the concentration of the silver, to the silver sulfate, or to the silver ions, or whatever type of solution we have in here? Come on, guys. Well, let's just say the silver ions. Okay. If I allow this to be exposed to the atmosphere, and the volume goes from 100 milliliters to 50 milliliters, what's going to happen to the concentration of the silver? Will it go up? Will it go up, down, or no change? Let's think about this. The solution is saturated. That means that solution can no longer hold any additional ions. So as this water evaporates, okay, goes from 100 mils to 50 mils, what should I witness within the beaker? Well, since it's a saturated solution at 100 mils, it's still going to be a saturated solution at 50 mils. So hopefully you said the concentration does not change. However, we should witness something taking place, or recognize that something is forming in the bottom of our beaker, and that's a precipitate. The reason why is because that solution can only hold a certain amount of ions in solution, and once that water is evaporated out, that solution can no longer hold those ions. So we start to see the formation of a precipitate. Actually, silver sulfate will start to form or crystallize out. All right, I'm running out of time here, and I think I ran through the different scenarios, and I explained all the different types of scenarios that are on here. If you have any questions, don't hesitate to ask. I hope this has helped.